Hey everyone, and welcome. I am so incredibly pumped to have you here for this explainer today. If you're the kind of focused learner who absolutely loves seeing the hidden scaffolding of the world, you are exactly in the right place. Today, we're unlocking what I love to call the Mathemagician's Toolkit. We're going to dig into 4 very specific mathematical investigations straight from the Cambridge IGCSE International Mathematics source material. And look, we aren't just going to sit here and memorize formulas. No way. We're going to develop some real, true mathematical intuition by seeing exactly how numbers flow, how shapes interact, how graphs physically morph, and finally, how all of this abstract magic actually models the physical reality around us. Let's dive right in.
Okay, so here's our roadmap for the explainer. We've got 4 main stops today. First up, cracking sequence rules. Second, taking Pythagoras beyond his standard squares. Third, transforming trigonometric graphs. And finally, the Ferris wheel model.
All right, section 1, cracking the sequence rule. Let's find some hidden logic in numbers.
Imagine you've got a series of numbered balls lined up in a row. Now, they aren't just random. They actually follow a very strict hidden set of instructions that dictates exactly what the next number is going to be, right up until the sequence abruptly stops at the number 1. Just take a look at the sequence we have here. We start with 25, then 26, but then it drops to 13, then back up to 14, down to 7, up to 8, down to 4, then 2, and boom, it stops at 1. I want you to just pause for a second and really look at those transitions. What exactly is happening when we go from 25 to 26, but then from 26 all the way down to 13? Can you actually spot the rule before I give it away?
Okay, here is the hidden logic, and it's beautifully simple once you see it. The rule alternates entirely based on the nature of the number itself. If you're looking at an odd number, like our starting point of 25, the rule is simply to add 1. That gives us 26. Now, 26 is an even number, right? The rule for even numbers is to divide by 2, which drops us straight down to 13. 13 is odd, so we add 1 to get 14. 14 is even, halve it to get 7, and it just keeps going like that until the sequence hits 2, which is halved to 1, triggering our end condition. It's just a brilliantly simple dual operation machine.
Now, what's really cool here is how such a simple rule opens up these massive, complex questions. Honestly, this is where true mathematical intuition is forged. If you know the rule, could you reverse engineer it to find the absolutely longest possible sequence, starting with a number under 100? What about under 1,000? Is there some deliberate strategy you could use to guarantee a long sequence, maybe by targeting specific powers of 2? These kinds of extension questions from the source material are the exact mental heavy lifting that turns a beginner into a master. It really pushes us to think way, way beyond just one isolated sequence.
Moving right along to section 2, Pythagoras beyond squares. Let's reimagine a classic theorem.
So let's grab our next tool and see how this builds up our geometric reasoning. We all know Pythagoras' theorem, right? A squared equals b squared plus c squared. But think back to what that actually represents visually. The standard textbook explanation shows a right-angled triangle with perfect squares drawn on each of its 3 sides. The idea is that the area of the largest square, the one on the hypotenuse, our a squared, is exactly equal to the area of the other 2 squares combined, b squared and c squared. That right there is the absolute bedrock of classical geometry.
But, and here's the really fascinating twist from the investigation. What if we don't use squares? The source material asks us to draw a right-angled triangle, grab a pair of compasses, and construct a semicircle off of each side instead of a square. Then, by measuring the diameters, we actually calculate the area of those 3 semicircles. The big crucial question is, does the area of the semicircle on the hypotenuse still equal the sum of the areas of the semicircles on the other 2 sides? Basically, does Pythagoras still hold up? And what if we swap those out for equilateral triangles or some other regular polygons? It completely challenges our reliance on the literal square in a squared, and it totally opens our minds to broader geometric proportions. Pretty wild, right?
All right, section 3, transforming trigonometric graphs. Time to manipulate the cosine curve.
Speaking of shapes and proportions, let's pivot over to graphical manipulation. We're going to visually deduce how altering just a tiny part of a mathematical equation totally changes its physical shape. So comparing these 2 curves, let's assume the base function, that standard wave you see in blue, is f of x equals cosine of x. Now, the red curve represents the function f of x equals cosine of b times x, where b is just a constant multiplier tucked inside the function. I want you to direct your attention to exactly how these curves differ. Notice they both start at the exact same peak on the y-axis, but they fall and rise at completely different rates along the x-axis. It is just a brilliant illustration of how a single constant can stretch or compress an entire wave.
Let's put these side by side so you can really see the effect of that constant b. On the left, look at the red curve completing multiple full cycles, up, down, and back up again, in the exact same space it takes the blue curve to complete just one single cycle. Then over on the right, the red curve is stretched out much wider, taking far longer to complete its cycle compared to the blue one. So that constant b directly dictates the frequency and the wavelength of our graph. A larger b basically squishes the wave together, bumping up the frequency. A smaller fractional b stretches the whole thing out.
So the real magic happens when we apply this knowledge backwards. Say we have a blue curve and a red curve. The source challenges us. Can you act as the math magician here and actually deduce the exact equation used to produce the unlabeled curve? By just observing how many full waves of the red curve fit inside a set number of degrees compared to our standard blue curve, you can calculate that exact b constant. You are literally using visual evidence to reverse engineer the algebra. Let me tell you, it is incredibly satisfying when that finally clicks in your head.
Finally, Section 4, the Ferris wheel model. We are bringing geometry right into the real world.
For our last investigation, we're taking all that abstract trig we just learned and we're applying it to a physical, rotating object, a Ferris wheel. Let's get our baseline parameters set up. We are looking at a circle with a precise 5 centimeter radius. Right below this wheel is a perfectly horizontal line, which we're going to call xy. This line is tangential to the circle at the very bottom, a point we'll just call P0. So essentially, at P0, the wheel is resting right on the ground.
So here is the actual problem we need to solve. Imagine a passenger car at point P1, which is hovering at a 60-degree angle from the center. And there's another car at point P2, which has rotated way around to a 170-degree angle. Our job is to calculate the exact vertical distance of P1 and P2 from that baseline ground level, xy. And to find these heights, we have to perfectly merge our basic geometry with our new trigonometric toolkit.
Okay, let's systematically step through the logic on this. First up, we identify our center point O. Because the radius is 5 centimeters, we already know the center O is exactly 5 centimeters above our ground line, xy. Next, we plot our 60-degree angle right from the center to find point P1. Now here's the trick. We form a right-angled triangle inside the circle. The hypotenuse of this triangle is just the radius of the wheel, so 5 centimeters. Using our trig ratios, like sine or cosine, depending on exactly how we drew our triangle against the axes, we calculate the vertical offset of P1 from the center O. Finally, to get the total height from the literal ground, we just add or subtract that offset to the 5 centimeter height of the center axle. Boom! It maps perfectly to physical reality.
Think about what we've actually accomplished today. We found the hidden rules in number sequences, we absolutely broke Pythagoras out of his standard squares, we manipulated the literal physical shapes of equations, and we calculated the exact real-world height of a Ferris wheel car in motion. All of that with just a few key mathematical concepts. So I'm going to leave you with this thought. If you can mathematically model a Ferris wheel, what other physical rotations or patterns in your daily life can be unlocked with this Math Magician's Toolkit? Seriously, look around you. The math is literally everywhere, just waiting to be explained. Thanks so much for joining me on this explainer, and keep learning.